Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. We have just started our discussion on superalloys, which is one of the best performing high temperature alloy compared to several intermetallics like aluminides, silicides, so far, and let us say the high temperature martensitic steels and so on. So, this superalloys has already shown their great potential, and also these alloys are already used in gas turbine engine, where the performance of all these material are assessed in terms of turbine entry temperature. Because in this turbine section the blades are required where both stress, temperature and degradation in terms of oxidation are important properties to consider. And even though there are several materials has been discussed so far, all these material and their performance has been summarized by considering this Larsen-Miller approach to rank the creep performance during service life. The performance of the material alloys has to be analyzed. Now, today we will start the discussion on nickel based superalloy. However, among this whole periodic table, why nickel is chosen as a base element, that we will try to justify, because any alloy development require finding a base element and choosing some other elements in order to enhance the properties in terms of some strengthening by some incorporating other phases, or let us say to protect the alloy from high temperature oxidation. And so far we have learned that aluminum, chromium and silicon, these are the three elements that provide protection, because aluminum from alumina, chromium for chromia and silicon from silicon dioxide. So, let us try to start our discussion with this topic, that why nickel is used as a solvent in these high temperature alloys, that is a superalloy, that is the topic of our interest, and we need to understand or justify the role of nickel. Since creep has been discussed a little bit regarding the high temperature performance of aluminide and nickel containing alloys, and also some sort of thoria dispersed tungsten and so on. So, the creep shear rate, that is simply expressed in terms of the gamma dot, that is the rate, that is why it is rate, and with a constant and their exponential. This is basically a very simple Arrhenius type of equation that we already know. So, basically this creep shear rate is proportional, it shows some proportional relationship with the volume diffusivity and the activation energy. Here the activation energy is expressed in terms of QV. So, that is the volume diffusivity, the activation energy, and R and temperature. And this means that we can take very different types of metals or elements, let us say BCC elements, FCC we can categorize in terms of their structure, because there are different voids, and that void are basically the pathway for diffusion of those other alloying element. And on the other hand, the self diffusivity has to be also considered, and we already know that the the diffusion required for creep and the self diffusivity, they have some close link. So, here if we need to normalize the creep shear rate, then we have to consider the melting temperature of a material or alloy or let us say an element. So, here we divide this parameter by melting temperature, and the dTm stands for the melt point diffusivity of a material. Okay. And so, before going to this equation, I show you one plot with melt point diffusivity meter square per second with different materials. So, the melt point diffusivity for a diamond cubic structure is very less than the BCC rare earth. Okay. So, you can see that the BCC transition metals and rare earth, they all are lying here, whereas ice has a relatively lower diffusivity than the BCC elements. Okay. Now, what are the competitors? Okay. So, in between we find a FCC metal, okay, or graphite. Okay. Now, oxides are here. So, it is for sure that oxide can be better for high temperature use, but since the toughness and all these other properties are very less and formability is also less, we can choose as a metal the FCC could be a better alternative. And now, if we take a consideration of this particular term, that is the activation energy divided by R into melting temperature, then we normalize all these different class of elements and different structures and materials, then we see that the activation energy for ice is higher, because this is just a reverse plot from the melt point diffusivity to the activation energy, just the opposite one. You can see the diamond cubic has the lowest melt point diffusivity, where the diamond cubic is lying here with the highest activation energy, normalized activation energy, whereas the BCC metals are lying here. Okay. Why we are always talking about BCC and FCC, we will learn within the next few minutes. And here are the FCC metals and graphites are lying. Okay. So, FCC is somewhat better in terms of using higher temperature, that is very clear compared to BCC or other elements. Okay. Now, let us try to look at some of the other aspect, because for high temperature not only the melt point diffusivity and activation energy for diffusions are important. However, what about ductile brittle transition? Means I can choose a base metal element, either BCC or FCC, and it should be able to retain its strength and plasticity, okay, in terms of avoiding some sort of catastrophic failure throughout the temperature of the use, operating temperature use. And let us say for a turbine, it will be cooled down, okay, sometimes in room temperature, again it will be used and so on. So, in that case, let us say a flight. Okay. So, when it basically landed, then everything is shut down, and again we start a flight by turning on the gas turbine engine. Okay. So, there is always a thermal fatigue. Not only that, there will be also a mechanical fatigue. So, in that case, the properties should be consistent with the temperature, not only the highest temperature, but throughout the range of the temperature is also a very, very important phenomenon. And therefore, we need to consider that, and let us have a look at a very basic mechanical metallurgy concept that we have learned quite a long time ago in the undergraduate days. So, here I show you some of the metals and their yield strength and reduction of area, which is basically an estimation of the plasticity. malleability or let us say the ductility with the yield strength and the temperature. Okay. So, different element have their different melting temperature, that is for sure. However, if we simply consider a temperature and its strength, means I am talking about a strength that is 0 time strength actually, means the yield strength. So, here nickel may have a low yield strength, however, it maintains the strength even let us say a pure metal as a pure metal up to 600. Whereas, if we think about molybdenum, tungsten, tantalum and iron, you see there is some common thing in between them, that is basically the BCC element. So, these element at room temperature or at minus 200 degree centigrade exhibit a very high strength. However, after just passing the room temperature, it basically falls, or let us say tungsten has the very high strength, but it simply falls with the temperature. Okay. Now, let us compare a very similar situation in terms of the ductility. So, here the nickel is lying here and all the BCC elements are here, okay, like tungsten, tantalum and so on. You see most of the BCC elements shows such kind of behavior. Okay. So, even in a low temperature, these BCC element simply loses its plasticity. Okay. So, if at higher temperature they are good, but it simply comes down, whereas nickel has a very wide range of very similar reduction in the area throughout a range from minus 200, where a plane has to land in a polar region, or to a very high temperature when it will be under operation. Okay. So, throughout this range it has a very similar properties, and this is very important aspect to choose a FCC metal for this particular high temperature solvent atom. Now, so far we have only talked about FCC metal and why a FCC should be chosen for high temperature. Is there any other aspect? Yes, we let us see the whole periodic table of elements. Okay. And very interestingly, I just plotted here the atomic number with the melting temperature. Instead of melting point, I prefer melting temperature in Kelvin. Okay. So, starting from hydrogen, you see there is a large peak where carbon is there, and now you understand why carbon is often chosen for high temperature material. This is one of the purpose. Now, let us come to a higher atomic number side. So, there are some peaks here. Okay. And you see these peaks contain vanadium, molybdenum, niobium, tungsten, tantalum and so on. So, what is common? So, yes, these are all BCC elements. Yes. So, BCC has a lower activation energy required for diffusion. On the other hand, BCC has higher melting temperature. So, which one should be chosen, or which one should be given more preference for high temperature material? Yes, I also told that a BCC element, these molybdenum, tungsten, if you expose to higher temperature in presence of oxygen, they all produces volatile oxides. Okay. So, volatile oxides cannot give you any protection from oxidation. Okay. And then we must consider some other things. However, it is for sure that this vanadium and these elements are lying in this 3D element. You see titanium, vanadium, chromium, manganese, iron. So, they all are lying somewhere here. So, here is the vanadium and chromium. So, titanium, vanadium, chromium, iron, cobalt and so on. So, this is 3 and this is the 4D. Okay. Here let us say zirconium, niobium, molybdenum, yes, and if you go towards this side, actually the d orbital electrons are increasing, okay, and a d orbital electron signifies actually that the bonding characteristic. So, like from here if you go towards this side, the melting temperature actually increasing. This is the symbol that if you go to this side, then automatically the bonding become more stronger, or let us say the cohesive energy is higher, that is for sure. Okay. So, on the other hand, the maximum melting temperature is somewhat at the center of these each rows. So, like here we have vanadium, and here we have molybdenum, and we have tungsten. So, these are the elements lying here. Now, these unfilled blocks, these are all BCC elements, whereas the slightly gray region are the FCC element. Okay. And from this theory, if we consider it as a theory actually, so probably these FCC metals may be better to choose, but you see these are all platinum group of metals, means platinum is very expensive, we cannot use it. Gold is also very expensive. So, for any industrial use, we unless and until it is not preferred to use actually. However, platinum heating elements are often used, or also platinum sensors are used. Okay. So, where we have no other alternative. Okay. But here mercury is a liquid. So, there is no use of it for these high temperature metals. Now, the melting temperature in each of these 3D, 4D and 5D rows, it also basically increases. So, the bonding characteristic are induced by the increasing the number of the d orbital electrons. Now, so we have only choice in this particular series actually. Okay. So, here we see that nickel is one of the element compared to palladium is also very rarely used, and silver is also in that platinum group of things. So, it is very quite expensive things element. And now, here the FCC elements are lying. Okay. Yes, platinum have a relatively higher melting temperature than nickel, but as far as I said that these elements are not preferred for the any industrial purpose. So, we have only one alternative, that is the nickel to be used. So, from because nickel has a 3D 8 or 9 electrons. So, nickel can be chosen as a solvent atom. So, now we understood that why nickel is chosen for any solvent atom in a nickel superalloys, because it is FCC structure, it is tough and ductile throughout the temperature range of operation. Now, it has a larger cohesive energy because of the outer 3D 8 or 9 electron, and it has a very low rate of diffusion and thermally activated creep, because creep is one of the most important properties to be considered as a material for high temperature, and the most important thing is that up to the melting temperature there is no phase transformation in nickel. Okay. And this is very important aspect, that there is no degradation of the properties or alteration of the properties as a nickel concern. Now, let us try to look at what are the other alloying element to be considered for strengthening nickel alloys, and for that we have to look at into the history of these superalloys. Okay. Because how these alloys has been developed with time. So, even around 1940s or so, or higher or earlier than that time, these alloys called bright alloys are developed. Okay. So, here we are only talking about oxidation corrosion resistance of nickel base alloy. I am not talking about in terms of their creep properties actually, where stress is there. Okay. So, here this bright alloy, the maximum use was something like 950, where chromium was added and also iron, and these are used mostly for heating purposes for some domestic appliances or industrial appliances. Silicon was little bit used, and let us say aluminum also used later on for a little bit higher application temperature, where chromium scale does not perform better. Now, with that time for the heat exchangers and let us say a carburizing atmosphere, or let us say oxidation environment, in both cases the same alloys, these inconel alloys has been developed. The inconel also contain here chromium, let us say in between 15 to 20% and some the iron chromium, that is why it is inconel. So, iron is also added and also some aluminum. So, along this direction, the mnemonic of one of the series that came up which used for let us say exhaust pipe, where also it need some good high temperature properties, where some amount of titanium is also added. And if we consider in terms of high temperature capability with considering creep. So, the benchmark was in between let us say 1000 hour of application and at a stress of 130 to 150 megapascal. Okay. So, in that particular range you see, even though mnemonic we consider as to be used let us say above 1000, but when stress is applied, the usable temperature range here is somewhat 800 degrees centigrade. Okay. And wasp alloy we have already talked about, where we have used the wrought alloys, and wasp alloy was very famous for these wrought alloys, or let us say directly cast alloy like Inco 713 and these alloys, or let us say some of these MAR alloys, or let us say directionally solidified alloys or CMX series. However, these alloy why has been developed later on to improve their operating temperature in terms in presence of stress is only the development of some processing condition considering some of the alloy addition. Means processing condition has been improved, because as a wrought alloy to cast alloy, where cast alloy we get equiaxed grain. Okay. So, equiaxed grain means whenever we will apply stress, here will be the break. Okay. However, if we take some directionally solidified grains, if we apply this is the stress direction, the grain boundary along this way normal to this direction are very less. So, these alloy such an microstructure will survive. So, these are I am talking about the grain boundaries. Okay. And if we simply make a single crystal where there is no grain boundary at all, then definitely they will perform much better, and these CMX series alloys are used these days on today for the blade application. But besides blade application, we can use these alloys. Okay. So, blade is a very precise thing, but cast alloys can be used. Okay. So, that is why this development basically come along from this bright alloy towards this from these 1940s up to today. And now, there are several elements you can always ask why, what is the role of these elements, or maybe some other alloying element has been added, what are the role of them. So, if we consider that, then there are very specific purpose of this alloy addition, where nickel is the majority of the concentration with nickel, that is for sure. However, for solid solution strengthening, which is one of the major strengthening issues, where molybdenum, tantalum and later on these tungsten and rhenium has been discovered to be added in this particular purpose. So, I have a solid solution strengthening, and one of the most important precipitation hardening is by the aluminides in the nickel base alloy. So, I have nickel 3 aluminum precipitate, which is required as a as a strengthening purpose. So, there we use actually aluminum purposely, so that we form this particular precipitate strengthening for high temperature, and also sometimes titanium is added there or tantalum. Okay. So, we prefer this kind of complex or other alloying elements to be goes inside the precipitate. Now, the third purpose of other alloying elements, like some amount of boron, carbon, these are very little amount is as read, okay, 0.2 weight% or less. Okay. So, to form carbide and strengthen the grain boundaries. And now, there is only two elements available for surface protection for oxidation, like aluminum and chromium. Okay. For much higher temperature, aluminum is mostly preferred. So, now you understood that in nickel, where majority of the alloying element chromium is added for a purpose that it will strengthen the alloy in terms of their surface protection, and we can go for, let us say, up to 20%. Okay. So, this will provide a protection up to 1000 degree centigrade, very good, because of the chromia formation. Okay. So, this is a nickel chromium purpose, and these are the directions shown in terms of the percentage of the element that has been added. Okay. And now, let us consider what are the other role and continue this, the wide range of microstructure that has been prepared in these nickel based superalloys. So, we have the gamma prime former. Gamma prime is basically the phase that is nickel 3 aluminum. Okay. This is a intermetallic phase, ordered intermetallic phase. In Inconel 600 or mnemonic series, in Inconel we do not add this, whereas the microstructure mostly contain these kind of precipitate at the grain boundaries, which are M23C6, M23C6. Okay. And these are carbide, and these carbides formed during hardening, or let us say or any treatment, or let us say during service itself, okay, and strengthen the alloy, where the carbide former chromium is required, which is replacing the M here actually. Now, for mnemonic we purposely add titanium aluminum to form this gamma prime phase, and also carbide formers are used, whereas in case of mnemonic 105 or woody mat, we have such kind of eutectic like microstructure containing gamma and gamma prime phase. Okay. So, these are the gamma prime phase in a matrix, that is the gamma nickel. Okay. Now, also in this Mar group of material, where there are some metal carbides MC that form actually, where tungsten and tantalum they are used. Tungsten carbide is like tungsten carbide here, you know the chemistry of this tungsten carbide. And for a CMX, these are the very advanced series used for blade, where such kind of unique microstructure of gamma prime phase embedded in a gamma nickel matrix are preferred. So, we understood that these particular element, where the element need to be partitioned in gamma, or element need to be partitioned in gamma prime, or element used for the grain boundary like boron, carbon, or let us say zirconium for the grain boundary precipitate strengthening purpose, or let us say these are the element which mostly contribute to be partitioned in the gamma prime or goes into gamma prime. Niobium usually do not use in nickel, but in iron nickel alloy superalloy niobium is used, where the element that goes into the gamma phase are these element like vanadium, chromium and so on. So, we already understood the role of addition of various alloying element in these superalloys. So, if I like to summarize today whatever we have discussed. So, we need a gamma matrix which is FCC structure, and this is a gamma nickel phase actually, and where there are several other alloying elements strengthened by solid solution strengthening. For solid solution strengthening, we add basically cobalt, chromium, molybdenum or rhenium, and these elements prefer to reside inside that gamma phase. Whereas, inside a gamma matrix we add a gamma prime phase. Okay, we prefer that this gamma prime phase should form, and this is a precipitate phase which is often coherent, and you understand the coherent precipitate require very high strength and strengthening effect is very good inside the gamma. So, this is a ordered FCC phase, and these phase particularly since it is nickel 3 aluminum phase and rich in aluminum means 25% aluminum is there. However, we also add some amount of titanium and tantalum to further strengthen. So, in case of nickel iron superalloy, here niobium is often used which is related with the formation of gamma double prime phase actually. Now, for grain boundary strengthening for at higher temperature we prefer the carbides and borides. Okay. So, here to form carbide tantalum and hafnium are used for MC type of carbide, or let us say 0.2% carbon is added which will form the carbide along with this element. However, M23C6 type of carbide, so these are also formed at the grain boundaries of gamma phase. Chromium, molybdenum and these elements are used. However, sometimes boron also used which will form boride with the chromium and molybdenum, okay, and reside in the gamma nickel grain boundaries. However, whatever alloying elements we have added for a very specific purpose, we must keep it in mind that there should not be any topologically close pack phases, because it enhances a embrittlement, and we have mu phase and sigma phase or Lavis phase, and these Lavis phase means basically X to Y type of phase and A to B type of compound that should be avoided. So, this is all about the superalloys in case of a nickel based superalloys and the alloying elements addition, and we will go into detail of the physical metallurgy in terms of microstructure, mechanical properties or high temperature properties specifically in the next class, and thank you very much.